Here we go again. um, in the last video, I basically left you off on a bit of a cliffhanger, I guess, where I mentioned that yes, there's this equilibrium between the S-trans configuration of butadiene and the s-cis configuration, which are basically the derivatives of your typical trans, your typical cis configurations of alkanes. Now, mind you, this is from the point of view of the single bonds, not from the point of view of the double bonds themselves. But this type of rotation actually has a little bit of a restriction to it, because you may recall when you have talked about Lewis structures, maybe even Vesper theory, in general chemistry, that single bonds are free to rotate 360, no problem. And that is true for the majority of single bonds because they're just made up of a sigma bond that is fully cylindrical in shape. However, to do that full rotation, or technically a 180 rotation, to go from the S-trans to the S-cis configuration, it actually takes a certain amount of energy to make this rotation happen. And to give you an idea, because you might look at this number and be like, well, okay, that doesn't seem too high, like that doesn't seem too bad of an energy, price to pay, because you probably have seen for reactions, you're talking about, hundreds, if not close to thousands of kilojoules per mole worth of energy. So you might think that this is, like whatever, this is nothing to be, concerned about. But if you do a quick analysis of it, you'll see that actually it has some connotations that need to be, understood. First things first, because this is a conjugated system, you do have these p orbitals that are all parallel to each other. But if you were to do the rotation, 180, you will, without a doubt, have to go through 90 degrees first before you hit 180 degrees worth of rotation. And unfortunately, when you do hit 90 degrees, you will fully break the conjugation, because at 90 degrees, the orbitals become fully orthogonal to each other and they do not overlap whatsoever. And of course, after you go past that point, then you bring it back to conjugation, but you have to pay the price of first breaking the conjugation just to make that rotation happen. And that's where the 15 kilojoules per mole of energy come from. And just to give an idea of what exactly that may be, there is a quick calculation that one can do to kind of get an idea of what kind of energy we're talking about. And it's basically an average energy, a thermal energy that tells you, roughly speaking, at a given temperature, in an environment, or even a reaction vessel for that matter, how much energy that may be. It's given by the Boltzmann constant, and then the temperature in kelvins, and it's roughly about 3/2. This is like an average value. It's not to be taken as like absolute temperature. It's more like an average, and even then, it's more like a an approximation of roughly what kind of energy you're dealing with. So if we stick with room temperature, 298 Kelvin, we plug in the Boltzmann constant, 1.38 times 10 to the negative 23rd joules per Kelvin, and then multiply by 3/2. The kelvins will cancel out, and you'll end up with a value of joules that is 6.17 times 10 to the negative 21. Now, even that in and of itself is not super helpful, because we have kilojoules per mole up here, we have joules down here. But you can convert this to kilojoules per mole various different means. You can multiply this by Avogadro's number and then change joules to kilojoules. You can also use the the Balmer constant to change from joules to kilojoules per mole. But either way, if you change joules to kilojoules and then multiply by Avogadro's number to get the moles in the denominator, you find out that room temperature, it's barely 1/5 the energy. If you want to be generous, 1/4 of the energy that is required to make this rotation happen. So what this means is that if you're just holding butadiene, in a flask, just at room temperature, you're not heating it up or anything, then the molecules are kind of stuck. Some of them are going to be in the S-trans configuration. Some of them are going to be in the S-cis configuration, mostly favoring the S-trans configuration because it has the least steric interactions, between the two alkene moieties. But they're kind of stuck, so that's important to point that out. All right, now One last thing, and this will be kind of like the prelude to the true preludes to the actual reactions, um, just so that we're on the same page. You can there's a couple of shortcuts that you can go about figuring out what the molecular orbitals are going to be for a given pi system. One way to do it is kind of like using these matrix boxes, where you kind of see how many times, basically from bottom to top on the matrix box, you increase the number of nodes represented by these segmented lines, and then the signs right here basically is telling you that the orbital is either in phase or opposite phase, right? So if you go from positive to negative, you're changing the phase, which will mean that shaded becomes unshaded, and shaded becomes shaded. As you look at the orbitals themselves, if you go from negative to positive, same idea. You change the sign, so you're changing the shading of your orbital. So this will be for ethylene because you only have two p orbitals, making the one pi bond, the one carbon-carbon double bond. So that will give you the two possibilities: one where they are both in phase with each other, one where they are out of phase with each other, right? And that's basically the molecular orbital we talked about in the previous video. But you can extend this to bigger systems. You can extend it to a system that has three carbons in a row that are technically conjugated, meaning that the three p orbitals are parallel to each other. And then the same story happens. You start with the bottom box or the bottom row where there is no nodes. Everything is in phase. After that, you start increasing the number of nodes by one. So what that would mean in a system of three p orbitals is that the middle p orbital will have to be fully omitted for this to work out. In essence, it plays no role in the valency of the molecular orbital. And by the time you get to the top row, you have to go from one node now up to two nodes. And so the only way to make that happen is if you keep changing the phase consistently, right? And as far as the orbitals are concerned, well, it will look like this. If they're all in phase, then you'll have the same shading on the top, same shading on the bottom. For the middle one, you'll have one type of shading on the left side, the opposite shading on the right side, and then nothing in the middle. And for the last one, you'll keep on alternating the shading as you go from left to right. So shaded on top, on the bottom, on the top. All right, if we continue the analysis, we can make a 4x4 matrix, and same idea. No nodes on the bottom row, one node on the next one, two nodes on the one that follows, and three nodes on the last one. And you may have already noticed that because we start with 0 nodes, we always end up with a number of nodes for the highest energy molecular orbital that happens to be one less than the actual size of the matrix. This is a 4x4 matrix. The number of nodes is 3. This is a 3x3 matrix. The number of nodes is 2. This is a 2x2 matrix. So the number of nodes is 1 for the highest molecular orbital. And then notice this, right? The bottom one, once again, the simplest one, everything is in phase. The next one, we have to make it so that it only has one phase. And so the node has to be in the middle. And if you wonder why it has to be in the middle, is because these things have to be as symmetrical as possible. So if you have 4 p orbitals and you're gonna have only one change in the shading, then you make it happen right in the middle to keep it as symmetrical as possible. And that's even more represented by the next row up here, because where we have to have 2 nodes, we place the node on the leftmost and the rightmost interactions, because that will give us the most symmetrical pattern, right? And so notice here that we have a plus sign on the left side, we have the negative signs for the 2 in the middle, and then we go back to plus. And then for the last one, it's kind of as simple as the first one, because here is always alternation, right? Plus, minus, plus, minus. So your orbitals will basically look like this: all in phase on the bottom one, out of phase as you cross the middle section right here, right? So shaded on the left for the first 2, and then unshaded on the right for the last 2. And then when you get to this one, the shading changes from carbons 1 to carbons 2, and from carbons 3 to carbons 4, as depicted by the diagram up here. And then for the last one, it just keeps alternating, shaded on top, then on the bottom, then on top, then on the bottom. Okay, so as you can see, you can continue doing this. I'll give you one more, the 5x5 matrix. So all in phase on the bottom, one node for the next one. So that means that the middlemost carbon is going to be totally out, out of the picture. It's going to have no valency in this orbital. After that, we get two nodes. So the way to make it symmetrical is to have the middle one be the one where the full changing happens, right? So notice that to the left of it, to the right of it, that's where the nodes are located. When we get to three nodes, the way to make that symmetrical is to have the middle one, once again, not partaking at all in the valency of these molecular orbitals. And then have the other two all the way to the left, all the way to the right. And then for the last one, it's just full-on alternation. So all the boxes are shaded, as you can see there. So your orbitals will pretty much look like this, right? All in phase on the bottom one. On the next one, you have the node right here, but one thing I should note, this is a mistake on my part, the orbitals here on the right side should be pointing down, right? So the shading should be pointing down, because otherwise you don't have a node. And then over here, the shading is the same for the first two, but then it changes on the third one. And then it changes again past the third one. So that's what you see right here for the middle box. For the next one, you have shaded on top, shaded on the bottom. So you have a node right here on the left side. The middle carbon is also not being included. So that's a node in and of its own. And then for the last two, you have a change in the shading again. And then for the last one, you have full-on alternation. So this might help you get to those orbitals. The other strategy, which is a little bit more painful, is just to memorize them, which I personally wouldn't recommend. But this is some strategies you can use to kind of get to, the orbitals, because we will have to look at what the shading is on one extreme and the other extreme of the molecule in connection to your HOMO orbitals, your LUMO orbitals, and the reactivity, which we will talk about in the next video. Okay, so I'll see you there to talk about Diels-Alder reactions. Bye-bye.